My name is Britt Stevens. I work for the National Center for Atmospheric Research in Boulder, Colorado. And I'm going to be sharing a little bit about the SCARGO project, what we're hoping to achieve scientifically, and what some of the operational sort of design criteria and modifications we're working on right now. So I mentioned I have an artist friend who drew this, and then the graphic designer sort of cleaned it up, but they took the skis off. So I'm hoping to add the skis if there's anything else you like. So I don't have escargot patches, but I do have RAF patches. So I work for the Research Aviation Facility at NCAR. We have a C-130 and a G5. So if I don't have enough, I can send some more to Eric, but after the talk.
You're looking for a retirement job.
Yeah,
right. Work on the airplane and fly the airplanes, the FMP-2000. Just saying.
Yeah. We have a hard time hiring pilots and flight engineers, and mechanics and technicians. So, okay, SCARGO stands for Southern Ocean Carbon Gas Observatory, and the overarching goal is to measure CO2 going in and out of the ocean around Antarctica. And we did a test deployment this past November and December, and this is a photo of our first rotator flight from Christchurch to McMurdo. Charlie Martin, who was one of our field staff, is operating the instrument, and it's in this Airdyne AS-20S avionics rack that was part of the whole system that IcePod flew, so it's just the rack, it's not the pod or the door or anything else. And it mounts just after the wheel well, sitting on the dual rail. So as I mentioned, I work for NCAR, which is a federally funded research and development center of the National Science Foundation, so we're, very integrated with NSF, and then we support a lot of, diverse things: supercomputers, ground-based instrumentation, climate modeling. But one component is the Research Aviation Facility. So it's NSF's airborne program, essentially. Actually, ourselves, and then there's a King Air at University of Wyoming. But our mission is to support these aircraft for the university community to request for doing atmospheric research. That's an older photo of our C-130. It has a snowflake on the tail that was taken from an instrument flying a cloud study. So it's an actual image collected from the plane. That's Denver in the background. But as Eric mentioned, we now just recently got the NP-2000s. I think that our pilots are working with somebody, I thought it was here, but it must be somewhere else, to get some training on those, because they're obviously new. The C-130, you're probably pretty familiar with the specs. Ours is a Q model, and without the skis, we get to 26,000 feet and can fly for about 10 hours, 2,500 nautical miles. And then the G5, when it was brand new, it was purchased brand new, and then went to Lockheed Martin for modification. So it had hard points installed on the wings. Here you can see it in the configuration where it's flying sort of 6 sets of 2 aerosol probes. They're not all populated in this photo, but those hold sort of aerosol probes. And then on the top of the plane, you can see pylons sticking up, and those are inlets for sucking air into the plane and making measurements of gas composition inside the aircraft. And then there are some large ports in the bottom and top of the plane for remote sensing instrumentation. And the G5 is really intended for going high and far. It can get to 50,000 feet, and it can also fly for 10 hours, but obviously goes a lot further in that time. So I study the global carbon cycle, that's CO2 flowing in between the trees and the atmosphere and the ocean. And why is CO2 interesting? Well, it's interesting because it's been going up. The black line here are measurements collected at Mauna Loa Observatory in Hawaii over the past 60 years, with parts per million on the y-axis and year on the x-axis. And there's an online app you can get and you can log into and type in your birth year, and it'll tell you what your CO2 age is. So without dating myself too precisely, my CO2 age is about 325 parts per million, and my kids were born around 375 parts per million, and we're about to go by 420 at this point. And so because carbon dioxide absorbs infrared radiation, this is causing the planet to heat up, and that's a big concern. But in fact, it's not nearly as bad as it could be, and that's because the trees and the oceans are taking up about half of what we're emitting. So The red line here is a curve of what we would have expected the concentration to do if everything we burned from fossil fuels and cutting down rainforests had stayed in the atmosphere. And so the gap between those two lines is this sink. It's a great sort of service to society that the oceans and the land plants are doing, but we don't really understand the processes responsible for that uptake well enough to predict if they'll keep going in the future. So if you want to know how hot it's going to get, or if you want to say to keep it under a certain temperature, we can only burn this much gas, you need to know what those natural systems are going to do. So we do know that the ocean around Antarctica, the Southern Ocean, is an important sink. A sink meaning a region that takes CO2 out of the atmosphere. It's an important sink for the carbon we're emitting. The geographers sort of define the Southern Ocean south of 60. Oceanographers sort of think of it often more south of 45 south, so basically Christchurch and south. And this is a cross-section of the ocean over here from about 30 south to 80 south, and then from the top of the ocean to the bottom, showing what the currents are doing. And because the winds can blow all the way around Antarctica, they have this effect of pulling water up from below. They push the water away from the coast and pull water up from below. And that deep water has not seen the atmosphere for maybe 1,000 years. And so the main uptake process is just this physical equilibration, kind of like the CO2 in a Coke can is equilibrated at that pressure with the liquid. So because we're increasing what's in the air, it's slowly absorbing into the ocean, and water that hasn't seen that increase for a long time can take up more CO2. But it's really hard to actually measure and figure out because there are a lot of other things happening at the same time. The water that comes up is actually warmer than the air, and if it sort of hangs out or goes south, it cools. If you've ever left a soda out in the sun in the summer and cracked it, you might have noticed it's a lot fizzier, so the amount of CO2 you can dissolve into liquid is less when it's less when it's warm, more when it's cold. So the cooling of the water wants to suck CO2 out. If the water flows north and it warms, that makes CO2 want to come out of the ocean. And then at the same time, you have all this algae that's growing every summer, taking CO2 up out of the water in the air. And then that algae dies and decomposes, and the CO2 is released back to the water. And when that water comes up, you can have this biological signal. So there are all these opposing processes, very complicated system to measure and to model. And then we also know that it's changing in response to climate change. So, given the few measurements we have, it's a hard situation to figure out. It's also very hard to measure because of how variable it is. If a lot of research has been done from ships or from buoys floating around, but if you're just measuring in one spot in the Southern Ocean, it can be very different than a place a little bit away. This is a picture from space of chlorophyll averaged over the summer season, and you can see it's very patchy. Some regions, particularly down current from Drake Passage and Chile, has got a lot of productivity, and then between Christchurch and McMurdo, you see these big patches. So there are not very many oceans operating in this region doing research, and very hard to extrapolate from those measurements. So the aircraft provide a really unique way to measure what's going on. As the air blows around Antarctica, it sort of collects all of the signals of uptake or emissions and averages them. So if you measure gradients in the atmosphere, they're sensitive to the entire Southern Ocean. So we've known this for a while, and we've managed to get some dedicated research aircraft to do flights. This is showing flight tracks from 3 different campaigns. So probably, if you didn't already know this, getting money from NSF, it helps if you have a catchy acronym, and sort of charismatic animals work well. So Hyper was the kind of original nickname for our G5, and so the Hyper Pole-to-Pole Observations campaign was something that I was a co-PI on back in 2009 to 2011. Those are the blue tracks, and we flew up and down the Pacific 5 times over 4 years. The plane goes up and down continuously to sample the vertical gradients from a few hundred feet off the ocean surface to to the sort of the upper troposphere. Then in 2016, we did a dedicated campaign out of Punta Arenas called Orcas, where we were doing similar types of flights, but just all around the Antarctic Peninsula and Drake Passage. And then there was a NASA project that I was involved in on the NASA DC-8 that flew similar to Hippo, but it came back up the Atlantic doing these global surveys. But in sort of by combining all of these, we got enough flights over the Southern Ocean to get sort of a seasonal picture. This is just a cross-section view of what those flight tracks look like. As I mentioned, the plane's just profiling continuously from the surface to, we'd usually stop around 30,000 feet to stay out of the air traffic lanes and then occasionally profile higher. So this Orcas campaign, you can see, was a lot denser sampling over a much shorter period of time. And from that project, we were able to map CO2 in the atmosphere. So now this is altitude on the y-axis, latitude on the x-axis, and the color is CO2 concentration. So the dark green is low CO2 concentrations and the red is higher. And we observed this really strong gradient with lower CO2 near the surface and at higher southern latitudes, which was reflecting uptake of CO2 by the ocean during summer. So that means that during summer, the biological effect of all the algae growing is outweighing any sort of warming effect of the ocean, which would be driving CO2 in the other direction. So this was a paper that the SCARGO PI team published based on these results. It's sort of the same people who were involved in this study as then ended up proposing SCARGO, because the analysis we were doing for this really showed us that you could use airplanes to learn a lot about the system. This was so you can use this gradient from low to high to estimate the rate of uptake of CO2. You have to use models of atmospheric winds to sort of convert those two things. But we got this estimate in the black bar here of how much CO2 is going in the Southern Ocean in summer. It's about 500 million tons of carbon, which is a fairly big number. I'm just highlighting here in the brown is an estimate that came from these robotic floats that NSF also funded to be deployed all around the Southern Ocean. And they measure pH of water, and then there's a conversion from pH to CO2 that's a little bit dicey. The other thing that's hard about the floats is that you can never calibrate them again. You chuck them in the water and they live for a couple of years and you never get them back. So at the same time that these people were, jumping up and down saying, "Oh, we think CO2 is coming out of the Southern Ocean," we were getting this result that said, "No, it's actually going in." So it's still kind of an open area of research, but a lot of interest in getting these measurements to really nail down the answer. So our goals of SCARGO primarily were so the previous flights were sort of a snapshot in time, and we had this question about how representative they were, if it was just one weird year, and then also, how do things evolve over the season. So the goals were to try and measure over a full summer season from November to February, and then to do it over multiple years. So specifically, the proposal spanned three summer field seasons. And then we had this goal that was, it really came from NSF. Our program manager at the time was pushing and soliciting proposals to do science on the LC-130 aircraft because, it's this potential resource. There are very few planes. It's very expensive to get research aircraft down there. So to try and figure out if we could do sort of scientific research from the operational flights that were already being planned. This is a figure from our proposal where it's a computer model prediction of what that field of CO2 looks like. The color scale is now different. It goes yellow to purple instead of red to green. But these were the flights that we put in our proposal, and that was the same program manager told us, well, you should propose dedicated flights. So we'll take the C-130. You can measure from Christchurch to McMurdo, and you can measure from Christchurch to the pole and do a dip. The other little catch in this process was the program manager wouldn't let us talk to you. We were writing the proposal. It was all filtered through the program manager, and I'm not sure talking to anybody. NSF sort of decided that was going to be really expensive to be flying mostly empty LC-130 for 8 hours. It was technically feasible, but so here's just a brief timeline. We proposed in 2018, we were funded in 2019, and shortly thereafter we submitted this paperwork. With some interaction with Walter Holman, we latched onto the idea of doing the measurements from this rack that attaches to the side of plane out of the way of the pallets. The idea was to, rather than displacing an entire pallet on the floor, to be off to the side. We submitted for approval of that, and then COVID happened, and it took a while getting through the SPO. So it was a couple of years before we finally had approval to do a test phase here. So this was March of 2022. But yeah, that was super helpful. So thanks to everyone who helped out on that sort of week-long effort. There was some weather, some maintenance, but we got a couple flights. We got one short flight and then one flight that was full length, and we were able to get enough data to support the full approval, which came through in around August of 2022, and then we did the test deployment in November and December. This is that rack without any covers on, so you can see what we're flying from top to bottom. We have a laptop, a UPS, power distribution unit, and then the gas analyzers. And it's an off-the-shelf instrument, but we have to sort of calibrate it and do some things to it to push it to its limits. There's a valve that can select outside air or air from one of these calibration gases. We have our own GPS receiver, so we don't have to interface with the plane in any way. The antennas on the hatch that I'll show in a second. Then we fly a couple compressed air cylinders with, it's just air in there, but it's air that we know the CO2 concentration really well. That instrument also measures methane and carbon monoxide and water vapor. So the main focus is CO2, but there are some other things we can learn from the other gases. And then the bottom is a pump to suck the air in. This was, I won't dwell on this too long, but it wasn't, totally roll on, roll off. You had to pull the dual rail cover and put the space down. You had to pull a stanchion that holds some seat parts and put this outboard support in. So that required help from the maintainers. And then the rack loads onto a hand truck, which then sort of tips into place, and then you have to bolt the rack down in a couple other spots. So it was a fair amount of work to get it in and out of the plane. That picture on the left I showed you already. The one on the right just shows, at least for that wooden luggage crate, I'm not sure what you call it, there's enough clearance that it can go in front of our rack. And then we get our air from a modified forward escape hatch. So this is standing in the cockpit looking up. It's a company that makes these for antennas and things, but we just have a few tubes sticking out, and you can see a zoom in of what we have two in case we ever want to compare them to look for any sort of surface effects on our measurements, or also if we ever want to add another instrument into our rack and need to pull more air. So we pull air down this big long tube to our instrument. This yellow line is sort of tracing how that worked. We've tried different routings, and that's what we settled on. This is a picture from the test flight phase. This is what happened last year. So NSF had originally given us indications that we could go and fly all the way from November to February. Unfortunately, they didn't really engage the ASC cargo planning team until very late in the process. And when they saw what we were hoping to do and thought about this requirement to have an egress lane in front of our rack and the need to then pack the pallets in position 5 with a cutout, they sort of threw up their hands and said, "Wait, this is going to be a big impact on us." So we sort of got de-scoped about a month before going, and then we were, at the gate in San Francisco having a beer when we found out that this 2-week COVID shutdown happened, the pause. And so we went home and came back. And at that point, as you all probably remember, things were behind and there was a lot of strain on the system. We did manage to get 8 flights in. Went back and forth between Christchurch and McMurdo 2.5 times, and then we did 3 pull trips, including one with a sort of test dip, and then we were still pushing while we were there to get to fly through January. But mid-December they finally sort of pulled the plug and said, "Nope, you got to get you guys out of here before the end of the year." Despite the reduction in scope, it was a successful test of operation. So a huge thanks to the 109th and everyone who was there. Dave played a big role. Wayne, who's not here, helping us get the instrument on and off the plane and figuring out how everything was going to work. But as I mentioned, it was successful in the sense that we figured out how to operate, and we learned a lot about how to get our equipment on and off the plane and how to try and mesh into sort of the cargo planning system. But we did identify stresses around this need to pack pallet number 5 with a gap. So I'll talk about. So that's partly the main reason why I'm here today, is to test out a new rack, and I'll show that at the end. Here's just a few quick looks at what we measured. These are just the flight tracks we flew during the season, just color coded by day, so you can see the 8 flights that we achieved. These are vertical profiles of carbon dioxide divided up into profiles over the pole, profiles over McMurdo, and profiles over Christchurch, with altitude in feet on the y-axis and CO2 concentration in ppm on the x-axis. So you can see over South Pole and McMurdo, there's this really kind of clean, the profiles are really clean, there's not a lot of variability. The strong sort of pollution sources or trees are a long ways away. Whereas over Christchurch, you see much more variability, and that's because you're seeing air that's recently, interacted with cars or power plants or trees, and those tend to have much stronger impacts than sort of local impacts than the ocean does. When you average over large areas, the ocean is still sort of on par. So if you look closely, you can see that there's sort of this right tilt to these profiles, so there's more CO2 high than low. It's maybe a little bit more clear over the South Pole. This is now just a color-coded map of all of those concentrations. So blue is low CO2 and red is high CO2. So you can see, over McMurdo, there's a clear signal of less CO2 down low, and over the South Pole, that's driven by this large-scale ocean uptake. The way we analyze these data is using a box model where the boxes are drawn to be parallel to potential temperature, and the reason we do that is because it is related to how the atmosphere mixes. So air is more dense when it's colder and it's at lower altitude. So these are essentially lines of constant density, and the storm systems that come through will tend to mix air sort of along these lines. So you can this is an easy way to see why we want to fly from McMurdo to Christchurch, because the exchange with the ocean that's happening at, say, 45 south is really being felt in these bands of air up here that we only really get to measure if we fly that either the rotators or the NSF flights to Christchurch and back. If we just do the flights to the pole, or just say vertical profiles over McMurdo, we would kind of be confined to only say things about fluxes south of around 60 south, and we'd like to be resolving signals from fluxes all the way up to 45. This is just a fun little surprise, and I like showing it because I don't know the answer, and I'm hoping somebody can tell me. But on 3 different profiles, this is now the same plots, but for methane, CH4, and they're really flat over the South Pole and over McMurdo, because there really are no sort of known natural sources of methane. So it's south of land. It goes down every day by sort of the same amount, and that's because of photochemistry. So sunlight is causing reactions that lead to a hydroxyl radical, which can react with methane, and that's what's slowly decreasing the concentration. So it's sort of like a rainbow here, going from purple to red. But 3 times going in or out of McMurdo, we saw these spikes. So there's a green spike here, an orange spike here, and a red spike here. It may not seem like much. It's 10 parts per billion, but those are really big signals, and we don't know where they came from. And I did an analysis of the winds, the wind directions, and the course resolution wind fields I had seemed to think that it was coming from somewhere different each time. So we're working to try and get these high resolution models and see if maybe one idea is it could be coming from the waste treatment facility in town, and we just happen to sample it. Yeah, or Erebus, but I'm not a volcanologist, so I don't know if methane would be expected to come out.
Seal colonies?
Yeah.
They're all beached up on the ice margin.
Yeah, exactly. These are all great ideas. I don't know. We need a map of the seals. So yeah. Most things, like if we flew through our own exhaust, which we do sometimes on these research aircraft, you would see CO2 spike at the same time. So the CO2 is not doing anything when methane goes up. So this is somehow concentrated methane source. So you can see over Christchurch.
What was served at the chow hall that day?
Yeah, there you go. That's a good question.
Burritos.
Well, it was December 28th. It wasn't quite Christmas. But this is kind of the fun of going out and measuring something in the real world, because you often see things you don't
Problem with
expect.
Christchurch is you have so many cracks in the soil because of the earthquakes.
That's right. That's
You
right.
have a lot of methane release from decaying
Yeah.
things down there in the sediments. It's exposed during the earthquakes.
Oh, that's interesting. I hadn't thought about that.
Yeah.
There's a big agricultural methane source in New Zealand as well,
Yeah.
and that air is you've probably seen Australia as at the upper levels more than
Right.
you're seeing New Zealand. But yeah, so for CO2 you would see sort of photosynthetic drawdown signals. For methane you just see sort of spikes going to the right. So I think that's all I had to show, except this thing about our rack went flush to the edge of the dual rails, and this is what the a fully cubed out pallet looks like. And on that particular flight, there wasn't one in position 5, but those pallets could not go there. So this is the rack we brought today, and we spent some time this morning staring at pallet position 1 in this region. And I didn't know this at the outset, but it turns out displacing an entire pallet number 1 is a lot better than displacing 14 inches of pallet number 5 in terms of the cargo loading. So I'm really optimistic about this this new approach. And yeah, I had these are all the questions, and I think we got almost all of them while we were standing out there answered. But we'll be following up with the few others. I'll stop there. Thanks for your attention.
On your end carver, what's on the outboard pylons?
Yeah.
Fuel tanks on the inboards. What's on the outboard?
So one of those, the inboard ones are actual fuel tanks.
Yeah.
So that's an actual fuel tank. It's used as, and this is I think might have one day been a fuel tank, but these are empty. They're modified to hold instruments. So they don't. There are not a lot of instruments that use them. We had this thing, a LiDAR, scanning aerosol backscatter LiDAR that goes in one of these positions and could rotate and could look up or look down. That instrument's been retired. The G5 has large pods that are sort of like F-16 fuel tanks that have been modified. That similarly, it's hard to get people to engineer into that footprint unless they really need to. So we have a radar on the G5 that's a cloud radar that goes in the large pod, and colleagues of mine are trying to develop a chemistry instrument that can sort of take advantage of being out on the wing, so it doesn't have to suck air. And but you can see here these are they call them PMS cans because the company is called was called Particle Measuring Systems, that makes aerosol probes. They tend to be, two miniature probes with a laser beam and a mirror, and it bounces it back and forth. So that's the sort of thing that gets mounted out on the wings. Yeah. So, yeah, happy to take questions. There's I anticipate another very interesting talk, so happy to.
Do you guys do any work with the WB57 platform?
So we used to have a WB57. That was before I was there. And then that got moved to Wallops. And so the plane that NASA is currently flying for atmospheric research used to be here. So we do have scientists who go fly on NASA campaigns. Like I was on the DC-8 for that project. And so there are people who go. And those instruments, of course, have to be totally autonomous, and they get sort of loaded up into the belly. And the higher you go, sort of the harder it gets, because it's so cold. When you come back down, everything gets wet from condensation, and you have to decide whether you're going to put the entire instrument in a box that's then sort of pressure controlled and dried. It takes a lot of engineering to do that. Or other people, they just turn it off before the plane comes down, and then the whole thing gets soaking wet, and then they just let it dry out for a couple days before flying. So going to 50,000 feet is, things are a lot easier than going to whatever, I don't know what a B-57 goes to, 75 or, 70.
Antarctica, great. Like you said, the Southern Ocean absorbs a lot of the carbon dioxide. Did you notice a vast difference in the different areas you were able to do the sampling from in the rate of absorption?
That's a really good question. So the based on we didn't get enough the answer is we didn't get, besides that one campaign where we were 6 weeks here, those others were all sort of one day, so we have like 5 flights at different times of year south of Christchurch, and it was really not enough to sort of answer what the zonal differences are. But when we were here, at the time of year when we were there, this is kind of what it looked like. If you flew right along the ice edge, you could see really strong uptake, and then out over the open ocean, it wasn't quite as strong. Earlier, we'd like to go back in November and December because this whole open ocean blooming in that as well. But as you can see, there are big zonal differences, and it has to do with the ocean mixing that brings up iron and other nutrients. So like right here, you have all this, but it's not so deep, and you can get all these nutrients. That's a good question.
Cultural loading too.
Yeah, right. Good
Like
point.
flows-
Yeah,
flows-
sorry.
flows
There's
out of the-
stuff that
You know,
blows
extra
off.
nitrates and nitrates.
Yeah, it blows
Yeah.
off of South America
Flat
into
edge right there.
that region as well.
So, this is talking a lot about biological uptake as opposed to
Yeah.
the water is self-absorbing.
Right.
There's
Um,
correlation.
Yeah, this is an average thing. They have it's really cloudy down there, as you know, so it's hard to get, a picture every day from satellites, but you can kind of piece it together. You get these gyres, these sort of circulating currents that will be coherent for, say, a week at a time, and those will travel around in the spring. If those are in the right direction to bring up nutrients, you get this sort of circular bloom that moves around. And people have ideas about going and trying to sample over those. There are other things that happen with all of this algae. They release chemicals, one in particular, DMS, which is a sulfur compound, which can then lead to, eventually gets converted to sulfuric acid, which can become a solid particle in the air and then have clouds condense onto it. So there's this feedback between the biology causing it to be cloudier that people have been interested in for a really long time. So there are, ideas for taking planes down and trying to study that process. But being able to operate from planes that are flying in this area already is really an attractive sort of possibility, because it is so hard to get one of these NSF planes. You have to write usually multiple proposals over several years, and then there's a reason why we haven't done any of those since 2016.
Small enough footprint, and it's really right for your eye.
Yeah, that's what's appealing to us. Plus, I should say, it's despite all of the NSF funding challenges and ASC's sort of being swamped and not being able to handle additional complexities, the Guard has been universally supportive, and can-do attitude is really impressive. So it's been really fun to work with this group, and I can't say thanks enough for all the help we got, because it's definitely we show up, we know it's not your day job to be putting some crazy piece of science on a cargo plane, but everyone is so cheerful about it that it's really nice. So we hope to make it as easy as possible, and we hope to get to do more of it.
Thanks, Brett.
JP, do you have?
Okay, great.
First the serious part, then the fun.
Okay, so good to see all of you, and thanks a lot for letting me in on your science presentation session here. It's my first time here in Scotia, so thanks a lot for all your work and for showing me around here and so on. It's fascinating. So I've been going to Greenland since 2004, but it's my first time seeing your home base here. I've been showing people around in camp in Greenland quite a few times, but this is I'm just mind-boggled by the size of your facility and all that you can do here. This is all new to me. But normally when you see us arriving in Greenland, then I guess this is what you see from the plane. That we are arriving here, and in this case JP, walking towards the camp that needs to be opened. And of course the reason that we want to go there and want to this remote location is that this is where we drill our ice cores, right? So we have this drill, and then we can go all the way from the top of the ice sheet and all the way down to the bottom, some 3 kilometers at some locations here in the central part of Greenland, and then get layer upon layer of old ice down there, but more than 100,000 years if we choose a good spot, right? So we can get this of old precipitation. And why do we want to do that? One of the reasons is that we want to both understand the climate of the Greenland ice sheet back in time, and also the evolution, right? So how did this climate impact the ice sheet itself? So if we just look at global temperatures from actual thermometers, we can go these about 170 years back in time. And then we can see that we have this trend, that we have something like, a little more than 1 degree warming if we look at the past 100 years here, right? If we want to look at the ice sheet evolution, then it is a much smaller time frame we have available. It's basically what we have from satellites. So if we look at satellite observations of the ice sheet, then we have something like 20 years. So we can have 20 years of data. And if we look in those 20 years, then we can see that the Greenland ice sheet here for the past 20 years has been losing mass all around the coast and gaining a little bit here in the middle. So basically it's getting a little bit higher, but narrower, much narrower, this ice sheet here, right? So we can see this is about, at some locations, something like 10 meters or so that we have gotten lower in the margin areas of the ice sheet over 20 years. And if we add it all up, then we can get a curve like this and convert this into how much sea level rise does that contribute to here. So in terms of sea level, it's not that much in these 20 years, it's 12 millimeters, right? But if you actually calculate how much you need to melt to do that, then you have this number in gigatons here, and that's actually cubic kilometers of ice, basically. So what you can say is that if you make some ice cubes of 1 kilometer either side here, then we have lost something like 4,500 cubic kilometers of ice from the Greenland ice sheet, if you add all these meters up all around, right? So it's quite a big amount. It just doesn't look like so much if you compare to the ocean or the whole ice sheet itself. But it's certainly measurable. But of course, we really want to know more, right? 20 years, it's not much data to have. And that's where the ice cores can help us. Also on the climate side, to go push this further back in time. And so basically the process of doing so is we drill an ice core. So we have our ice core drill. We go to the ice sheet and then we drill. And then we can cut some samples here from this piece of ice, and then we can do some measurements on it. But normally, before we do the measurements, then we need you guys to fly all these samples out again here, right? So we need to put them in boxes or so on and so forth, and then you take these precious samples here and then bring them to our lab. And the lab could look like this, but nowadays we are also getting a little more modern, so we're not only mass spectrometers, but actually using picaros like you do, just for the water samples as well, right? And this is actually the part of the science we do on ice cores that I'll talk a little bit about today, is what we can measure on the water itself, because of course that's the most common thing we have in the ice cores. That's water molecules, right? It's frozen water molecules that we have in the ice core. So it's nice to see what can we do with the most abundant thing we have in the cores. So what we want to measure, if we look at such a water molecule, then we have the oxygen atom here and the 2 hydrogen atoms, and we can give them with a little bit different weight. That's what we call isotopes. So we can have different isotopes of oxygen and hydrogen in the water. And if we say we have an oxygen atom that is a little bit heavier than normal, so the normal has a mass of 16 units. If we have an 18 unit instead, then this water molecule will be a little bit heavier, all in all. And that's actually, if you look in nature, then most of the water molecules are of the lighter isotopes, all of them, both the hydrogen and the oxygen. But there are some water molecules that, especially with the O18, you have like 2,000 of these for each million water molecules. So that has traditionally been the easiest to measure, to find out how many water molecules do we have with the O18 compared to the normal O16 that is light. And the reason that we really like that measurement is that it actually tells us something about the temperature when we get the precipitation on the ice sheet. And one way we can look at that and see it is that if we do an ice core and measure this O18, so now we have the O18 values down here. So these are the values we get. Then if we have less negative values, then that means warm temperatures. More negative values means cold. Then it's basically like a tree. So we have the depth here, 405 meters, 410 meters, so on and so forth. And then we have the summer and the winter and the summer and the winter and so on and so forth down there. And we can count annual layers by making this measurement. So in the tree, you have tree rings, you can look at them and see them. Here we need to do the measurement first. But then we can count the layers, then we know how old our core is. But also I hope you can see that some summers here seem warmer than others. So it's not only that we have the information on how old we are, but also how warm is each summer and each winter back in time. And one way we can check if this works back in time is that we can take a lot of ice cores here that have been drilled during the years, and that we can compare to weather station data in red here for the last 200 years. We're lucky enough in Greenland, it's actually been people measuring temperatures for 200 years. So this is the 200-year temperature record here in red. And this is the average of this O18 measurement in blue from the ice cores. So I hope I can convince you that this actually works pretty neatly, this kind of thermometer with the water isotopes. So we can actually see that we have the same variability in the temperature data and in the oxygen isotope data of the water molecules in Greenland. So this is a way we can say, okay, well, now we have tested it. We know for the last 200 years this works. Let's go further back. Now we have the ice cores, right? So basically, 200 years of data that shows us it works. Let's go back in time, thousands and thousands of years, right? Do the same measurements on the ice core. Let's get a climate history. So if you do so, then we can do this for many, many cores, because you have been flying up people from our group for many, many years, and we have gotten a lot of ice cores, so we can actually have some coverage here, right? Both from Greenland and Canada. So one thing I should just say here, this is a record. Ice core people, we like to go back in time, because that's when we get deeper, right? So sorry for turning the axis a little bit around. So this is today, 2,000 years ago, 4,000 years ago, up to 10,000 years ago here. And then you see, basically, if we look at this ice core here, pretty stable climate. And then of course we're getting out of the glacial period here, so this is out of the ice age. But the last 8,000–10,000 years, basically stable conditions, right? But what about the other cores? Story is suddenly not so simple anymore, right? So here we have the other ice cores from the other locations. And yeah, some of the signal looks similar, but if you look at the trends, let me show you the trends a little more. Now I take everything to 0 today and take the deviation back in time. Then it looks like this. What a mess, right? So I remember when I saw this curve, this figure the first time, and I thought, okay, so if some of you came and said, okay, Professor Bo Winter, can you please now tell us, after 50 years of research, 10,000 years ago, how was climate in Greenland? And then I would say, based on all our information, I can tell you it's either colder, the same, or warmer. I have a, I'm quite sure that you're laughing, but I'm not sure my funding agency would say, this is worthwhile, research to do, right? So, but on the other hand, it's always when we get results like this, that's when, as scientists, then we have to think, right? So how can this be that this is the results we have based on all these ice cores? So a little bit back to the drawing board as we speak. So this is basically one of the inventors of this method of doing temperatures, Professor Willy Dansgaard. So he published already in 1961 that if you walk around on the Greenland ice sheet and take a lot of samples around Greenland, then you can basically say that as you go north, then the values of O18 will be lower because it's colder. And as you go higher up on the ice sheet, the same will happen. So as you go up, then also the O18 values will be lower because it gets colder. As you go up, you gain elevation, right? So, and he had got these made from a lot of measurements, got these data, and we can confirm this again today. So if we have ice core drill sites here we have these O18 values that tell us something about temperature. Here we have the elevation of the drill sites. Then you can see basically almost a straight line down here, right? That as we go up, it gets colder. So what happened to our ice sheet back in time? Yeah, some of our ice cores are from the big Greenland ice sheet. 2 of them are from small ice caps that are drilled on mountain glaciers, basically. And what can happen is that this ice sheet here, when it was glacial cold, then Greenland was a lot bigger, right? A lot wider when we had the last ice age. Much wider. But that's the mountain that is determining the shape of this ice cap, right? Basically, you have it on a mountain, can't get any bigger. And we have some of these ice caps. One of them is here in eastern Greenland. We were there some years ago in eastern Greenland, the Rhineland ice cap. 2.3 kilometers elevation here, the fjord down here, and the thickness 300 to 600 meters. So not much you can change in shape or size of that ice cap. It's basically, if we look into it, it's a bathtub that is filled up to the edge here, right? So you just have this ice cap just filling up this whole plateau. We have a similar situation up here in Canada with an ice cap that's the same way. If we compare the O18 profile from these two, so the measurements here, then we get a very similar climatic history. So that is those places that cannot change their elevation. Then what we see is, this is today, and then some 10,000 years ago, it was somewhat warmer. And then, of course, going out of the glacial period, it was a lot colder. So, what can we do? We can say this is our climate, right? Because here we can't change the elevation. So we can say this is our climate history that we have over the ice sheet. But when we then see something different from that, then we can assume that that's probably because this big Greenland ice sheet was bigger or smaller back in time, it changed its shape. So the location where we drilled the ice core was higher up or lower down, and that gave us this difference in temperature. So if we again do this, if we look at these profiles here, then we can put in our climate reference on top, and then we can see that all the locations here in Greenland, if we go back in time, they were colder, so that means they were higher up, which is exactly what we would expect if we had this big ice age Greenland ice sheet that was much larger than today, and then it retreated during the Holocene hour warm period, when it went warmer. And if we look a little bit on the difference, we can actually say how much elevation change does that convert into. So how much did the ice sheet change its elevation at these sites? And it's actually quite a bit. If you go to Camp Century up here, it's about 600 meters. It was higher 10,000 years ago. Down here, it was about 400 meters. In here, 100 to 200 meters. And this is exactly what you would expect, because if you imagine you have this wide ice sheet here, and it then retreats, then out here, that's where you have the big elevation change, when the ice sheet starts to do like this, gets smaller. Whereas in the center, you don't change much. Then you can of course say, but can you really be sure that this is what happens? This is what happened based on these data. Couldn't it be something else? Couldn't it be local climate conditions just being different in one place and another? Is it really elevation, this? And that's where it's a beauty to work with ice cores, because we can actually measure more than just the water molecules. We also have air bubbles in the ice. So when the snow comes and settles, air is trapped. You can do that for measuring greenhouse gases back in time, but you can also just measure the amount of air that is trapped in the ice. And that amount is dependent on the surface pressure. So if you have a high surface pressure over your ice sheet, then you trap a lot of air. A low surface pressure, not so much. So imagine you are high up, then you have low pressure, right? And if you're low down, you have higher pressure. So the amount of air is also dependent on the pressure you have on the surface here. So here we have some samples from different elevations with different surface pressure. More air is trapped at the higher pressure. So we can then test and do these measurements and compare them to the elevation curves we have before. There's some scatter in the data, but if we smooth them out, then we can see that this fits. Here we have the elevation history. Here we have the change in the amount of air trapped. I've inverted the axis, so you can see here, this is lower, this is higher, just so that it fits. And exactly the same here at this Camp Century site, where we had 600 meters of elevation change. Don't have that much data from this old core, but it fits very, very nicely. So in that way, we can confirm that this is elevation change. And then, of course, the fun begins, because we can also reconstruct the climate. So now we have a climate history based on the weight chain measurements that from the cores that are stable elevation. And then this curve here, that is how many meters of change that we have in the ice sheet per century here at these locations. So how fast is this ice sheet changing its size? And what you can see is this, yes, when the temperatures were high, 10,000 years ago, then we had the fastest decline in elevation. So it goes very neat, and you can then say that what has then happened over the last 10,000 years, temperatures went down, and then we stabilized actually almost around zero change here for the last 2,000 years of the ice sheet. But of course, now temperatures are going up again. And actually, if I added the meteorological data that we have from the last years, then we would be above 2 degrees of warming here. So I would be able to draw a line in here. We are reaching the point where this ice sheet is bound to respond with changing its size and shape, right? So, so basically, with respect to the shrinkage of the Greenland ice sheet, it's not a fluke these last 20 years. Get used to it, because this is what we will see in the future as well, when we have the temperatures we have. There's no way around it. We can see that from the data from the past, that they tell us, with these temperatures, this ice sheet is not stable. So, get used to some water. Thanks a lot for listening. Yeah, any questions?
One thing I was wondering is, especially with Renland and
Yeah.
Agassiz one up in Canada, is there a correction for like proximity to where the ocean would have been too? Because I mean, you're in a more maritime climate too, close to there too. So how does that affect your temperatures?
Yeah, it doesn't seem to affect them that much there, because it's still, they're pretty far away, both of them. But you are right that that what could affect them is if you imagined, especially for the Canadian side, that you got so dry that maybe you lost the winter snow, because it was just so dry and so cold that you biased your sampling towards the summer. Then that would be an issue.
Yeah, 'cause I'm picturing if the Greenland ice sheet's bigger, right?
Yeah.
It's obviously farther from the ocean margin at that point, but then as things warm up, that ocean's creeping closer and closer.
Indeed. And that's also why it's difficult to push this into the glacial period. Because what I you can say that helps me out here is that I'm in our warm period the whole time. So this means that the sea ice and the ocean around Greenland has already, cleared up and broken up. But if I go into the glacial, then you're right, then I get into trouble here. Then I have to do much more careful analysis. Okay, then I think I'll leave it to JP.
Yep. I like the shades. Two cool guys. Open snow operation put in at E-Script this year. I just love it, and it just goes on because that little GoPro just went on so we can see all the people going out of the plane and everything. But I thought, why not take it from the perspective of the poor pilot and you see how you just dump the shit on the snow and just disappear, get lost, and then they stop, and then somebody comes and picks it up. Yeah. Anyway, it's just full of toothpaste. So, I thought it was a nice little other take on things. I will just make a short comment on what we have done this year, if I can find my doc. At E-Script, there it is. It's already open. So we'll just go up here. There we go, and presenter mode, and then we should be fine. I hope. Yep. There we have it. We start with the dome again. You know, it's a 4-story building on skis, right? So it's already a well-traveled building. It's traveled almost 450 kilometers. We went to E-Script because of one particular thing. We're drilling ice cores, as Bo mentioned, very much for climate. But there's one thing. What's been eluding us is to get a full, beautiful record of layered ice from the last interglacial, between the two last ice ages, 120,000 years ago. It's been eluding us several times. We have it, but it's always disturbed. And then we sort of gave up and said, okay, daughter came over, another, let's do something else to change. Let's drill an ice core. No, that's not something else, but the objective is different. This is color-coded according to the surface horizontal velocity of the ice. So if it's red, it's moving sideways real fast. If it's blue, it's standing more or less still. So we have a velocity map of how the glacier goes from the center out towards the ocean. But you have this long tongue, northeast Greenland's ice stream. And it's a zoom over here. You see this long tongue. And it's actually quite long because it's from here to here, it's about 700 kilometers. So it's a big thing. So we decided to find out or analyze what makes these ice streams go. Why do we have this sort of wedge of very fast moving ice in the middle of stagnant ice? So the thing about ice stream is, everybody knows what a mountain glacier is, right? You have this tongue of ice running through down to a valley. But imagine that valley, the sides are also ice. So you have a glacier running in a valley of ice. That's called an ice stream. So it's pretty cool. And the crazy thing is, when you cross, we drove from here to here, it's super flat. Everybody who's working with the monoline know that from the plateau in Antarctica and in Greenland, it's just flat. That's what we like best. As soon as we start to have a slope, we get worried. But here we had this funny thing that when we crossed into this stream here, crossing over the edge, I was driving in the last tractor in the tractor drain, and then the dome was on skis ahead of me, and all of a sudden that thing disappeared. And it reappeared again. It was a shallow valley. So there's, all of a sudden we saw structure here along the sides of this ice stream. This is where we decided to go. To find out, drill through, to find out what makes these ice streams go. And to back up that idea and to go do something, we did some mapping, and this is, again, the velocity field. The red is the ice stream, it's just a different cut. You see the north arrow. But this is the path of a radar plane that measure with an ice radar. So here you see a cross section of the ice stream, and you can see it looks like a tree trunk, like cut. You can see all the, it's not annual rings now, but it is during the ice age. There were about 26 climate flip-flops that changed the chemistry of the ice, and that shows up on the radar. And also volcanic eruptions will show up on the radar. So we could see that if we drilled down through this, we would get all the way down. Since we have all the other cores from Greenland, we could compare that, and then we could put ages on these layers. So we knew, hey, this is an old block of ice that's moving sideways. Why? What's the limit to it? So we wanted to get in there, and Knut Christiansson, he provided us with an elevation map to find out where to go. So these two yellow lines are the sides of the ice stream, and then the color coding is sort of the elevation, and this is me putting in the skiway because I wanted that skiway to be sort of in the saddle, not on the top and not in the valley. So you do that, and you can sort of mingle around. So we got a skiway at 0.23 degrees slope. As you probably some of you have heard before, we have these underground caves where they drill the ice cores, and we analyze the ice cores. We made them in balloons back in 16. At that time, the ceiling height was 5 meters or 15 feet. Then they started shrinking, and then COVID came, and we had to cancel 2 field seasons. So when we came back in 22, the ceiling was so far down, we had to bend down to go through, and quite a few of our things were almost crushed. But as you can see, when you have a snow ceiling, you can just cut it down with a chainsaw, knock the blocks out and remove them, and then you can get some height again. So that's how we saved the project. If it had been a wooden roof or a corrugated steel roof, we would have to abandon everything. You cannot cut that from below. That will kill you. But as long as it's snow, you can do it. We had, when eScript is there, it's also used as a logistical hub for others. So here we have a little Twin Otter visiting us, and they were doing a pre-survey, site survey on this northeast ASIC site of Screen Drill is going to do next year. And we might support it, we might not. It's not that we don't want to, but it has to fit into the organizational plans whether eScript is a factor or not. It's not undecided yet. But this is how the camp is looking right now. All the ice drilling and so on is going on in the underground caves over here. Those little tents are really important because that one is an elevator shaft and that one is an emergency staircase. So make sure that, yeah, you can get in and you can get out. And if a polar bear gets in, you can get out another way. We had a very unusual visitor. I have to tell you that eScript is at 8,885 feet. And it is 600 kilometers from the nearest gas station, if not more. So this little pilot driver there, he had some guts coming in there and picking up some fuel and going on. He crossed the ice sheet where it's about 1,000 kilometers wide. And as I'm told, those helicopters don't come with autopilots. So he has to be at the controls alone all day to do this. It takes a lot of guts. I wouldn't do it. But then again, he didn't have passengers, and he insisted, and he asked if he could get fuel. I said, yeah, if you come, you can get fuel, but just be aware of so-and-so. So he did. Otherwise, it's these guys, and you know them well. I would like to draw your attention to a fact that you can hardly see the skiway. Because in midsummer, when you groom it right, you don't get any sides to it. It's just seen from the side, you really cannot see it. But of course, if you're airborne, you can see the contrast of the fresh groomed thing. But from the side, you don't really see it. And you can see it's actually sliding pretty high. I mean, the front ski is up, of course it's rotating, but anyway. So that's a very good thing, but I understand that it's going to be a more and more rare sight to see ADOs in action. I understand that, but it's nice once in a while to see it.
I was on that flight. We needed it that day.
Yeah. Oh, you're sitting in the left seat there?
I'm behind the co-pilot.
Oh, you're behind the co-pilot. Oh, yeah. Yeah, you need that. That's. I think it's the 4th or 5th slide.
Yeah,
Yeah.
it was.
Yeah. And it's not because we didn't groom the skiway and we have all this discussion about hardness. Weather can do things to skiways at any time. So it's really touch and go, and have a chat with DC and the field leaders and the field operation managers to find out what is the situation today, what do we feel like, and how much is the urgency, because urgency also plays a role. We went into a red light district end of June because all of a sudden we started to get basal material up at a depth of 2,658 meters. Little pieces of stone came up. And that tells you, okay, now the ice is finishing and we're getting into some minerals down below. And we had a pre-arrangement with everybody who's interested in basal material that in order for us to preserve the luminescence properties of dating, you must not expose it to light. So it's like an undeveloped film. You have to pack it in black and keep it away from light. That's why it's a darkroom lighting, so they can do their luminescence dating. Because what we are pulling up now probably hasn't been exposed to daylight for 1 million years. So we were a little careful about that. And then our normal ice core drill couldn't drill anymore, so we switched to the rock drill. So you have the ice core drill here, which is a 4-inch drill, and then we just modified the bottom. We have the motor and everything, modified the bottom and put the rock drill on. You can see it's a 1.5-inch pipe with a grinding head. And then it's just friction that keeps the core inside. It's a much smaller core, but you can whack through stone. With patience, you can just go through anything. We call it a rock drill. And I did that, and then I never been so happy to write the word mud. And also wrote it with exclamation marks on our whiteboard in Kangarooswak next to our office the day it happened. This was in the beginning of July. And those two happy campers in dark room light, they are having this 1-inch, about 35 centimeters, 40 centimeters long, frozen bar of refrozen mud, or it looks like quicksand. So now comes all the stuff we have to analyze, going down through, we drill through the ice. Remember, we drill into rock in a place where the entire camp and the borehole is moving this much every day, right? So they were using that 1.5-inch pipe to go down and drill that. Trouble was, they lost the drill. They parked it down there. They pulled it up and the cable was empty, or the motor was empty. Then there was supposed to be pulled out by the 109s. Well, there were severe icing conditions, so that was canceled that day. So they went down, they had another day, they went down fishing, and they managed to fish off the drill. Now, what's really mind-boggling here is that you have this whole 2.6 kilometers lump of ice sliding sideways this much per day. And these guys parked a pipe, 1.5-inch pipe, with a threading. and they go up 2.6 kilometers. And then the following day they lower it down, and with the other part counter-threading, they actually manage to screw themselves in again and fish everything out. That's only possible if everything, including the mud, is moving. Otherwise it would be off. So I think the fact that you can catch a 1.5-inch pipe in a hole that slides sideways means everything must be still sliding sideways. So I think we just punched through the top of that quicksand that apparently is below the ice stream. And this is going to be something that we have to work on for quite a while, because it's going to affect all the models of ice streams, because we are standing on a block of ice that has absolutely no internal deformation. It's just sliding. So the green ice sheet right there is like a shipping container on a freight train. And we don't know what makes them go. And the reason why we really want to know it is because Bo mentioned the sea level change and the loss of mass of the green ice sheet. Trouble is, we can only explain half of the mass loss of the green ice sheets through melting along the sides. The rest is from the ice streams, and we don't know what makes them go. But I tell you what this is where this is going. Right now, the prognosis for instance, the city of Copenhagen, which is a medieval port city, so that means the city is right where the ships were docking. So street level height is, what, 10 feet? Yeah. Do we like to have a sea level rise of 1.5 meters, i.e. 3, 4, 5 feet? No, not so well. And then when I tell you that right now the best estimate from the international community is 2 feet plus minus 2 feet. That means in the next 100 years we can expect anything between 0 and 4 feet. Now, if I were an insurance company, I would like to know my risks a little better. So if we, through this model work, can narrow down the uncertainty to get a better value of future sea level change, that will be worth a lot of money in the insurance business, because they will get their premiums right. But right now, as things stand, I would not recommend you buying beach property in Florida. It is so exposed. There's no way you can do anything there protecting. In Copenhagen, they are already beginning to build a fence, a bulwark, a dam, so they can keep the storms out. Anyway, we had a great season, and I mentioned it yesterday. I just wanted to have a few things. Have you ever seen a skier doodle? Here's a skier doodle. Coming here from where? Oh, Goose Bay, YYR, to NA. Not applicable, but I know what it is. It says it there. So it comes up here, and then it skidoodles around, doodle, 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 and then off it goes, skier 01. And you know what? It has 2 partners there. What are they doing? They're also skidoodling around, because all 3 of them were diverted in the same day, because Kangar for once had shitty weather. And we could hear them standing down there. I remember we talked Tracy in front. Say, what the hell is going on? I just heard one passing. And then another one. What was going on? That was funny. It's a very rare occasion, I must say. So I just thought it was funny how we can trace everything going on with this modern stuff. But thank you for having the transponders on. It helps a lot for us. You become invisible when you go to the ice cap. Halfway to summit, gone. And you become visible on the way out. So as soon as the skier becomes visible, we know when we have to go and pick people up and be ready with our equipment. Yeah, it's a very special view, because this is taken from inside the cab of the tracked vehicles that we got out of the field this year. 2 pre-piston bully era PB100s, Flexmobiles. They've been on the ice cap for 34 years, and it was the first time ever they got dirt under their feet in 34 years. And I was asked to drive it out. No, we organized it so that we had a good driver driving them on, and I was here to drive it off in Kangar. But I thought, what a spooky view to sit inside a tracked vehicle and looking out inside a C-130, and then being asked to sort of trundle that thing out. That was a 1.5 inch to both sides, and then make sure it went. But it went well. thanks to loadmasters and aerial porters. And they're out now, and these two are now going, you can see it's a German tank. I hope you can see that. Anyway, these two are now in happy retirement. They're gone to the coast of Greenland, to Sisimiut, where the Arctic Engineering School is run by the Greenland and Danish government. So students are going to have fun with them, tinkling with them, repairing them, working them in Sisimiut. So that would say I'm very happy we could do community service here. That's a picture daughter sent in July 22nd. This was not an ADO required day of taking off. This is a skiway, and on a perfect day when it's properly done and the snow is behaving, that's the track of the main ski on our skiway. It's like a ballroom floor. And so we spent, those of you who have been at Arctic Planning Conference before, I have. I can tell you it's a circular discussion we have each year, how to measure and groom and what's the optimal grooming. Basically, a lot of grooming will just improve the conditions really well. Trouble is you'll lose it. Once the weather changes, you'll lose a perfect skiway, and it's really bad. Particularly when it's so good like this. Just wish you could keep it that way. The annual Row Club dinner was really fun again. So I just ran in. Yesterday we stopped by on the way from the meeting back to Saratoga Springs, and we just had a pit stop. And there was a guy filling his tires on the car, and he turned around and I said, "I know you." "Hey, JP, are you here?" It was Carmelo. and you really start to feel like community when it's like you're bumping into people on the roads and they start waving at you because you know you. Maybe I should consider becoming a New Yorker. I don't know. This is our main dome on top, and this is a novelty I want just to introduce to you. You know that one. That's an Iridium open port, which is an expensive but efficient communication system. This is where we have a polar bear radar. It was just taken down right now before you pack it down. That little thing, you probably recognize the shape. We also have it here in a portable version. Sitting right here, and this guy is happy because he has internet, big time. And there you see the two flexes before they went up. Starlink is a revolutionary system. It works for our purposes, and my wife's daughter also tested it at Müller Ice Cap up on Axel Heiberg Island at 80 degrees north. It works perfectly, but it's so spooky to Skype with her. She was sitting in the kitchen tent in the middle of a blizzard with a small Honda chugging away outside, and I was sitting back in our house in Copenhagen, and we were Skyping with pictures and images and things, and she was not alone on the web. There were 4 guys hooked up. That little thing actually took care of our entire camp. We took down the 2.5 meter satellite dish we have for VSAT, geostationary satellite. We always had our last 5-6 years. We could see no effect whatsoever on the output on our webcams or anything. So this is right now it's the last webcam thing from August 14th on our pull-out date. So we kept it running until the plane was on the ground. And see here is somebody's taking down the weather station and carrying it into the warm kitchen. Just to say that that's astonishing, and because it is available, it would be irresponsible of us who is organizing all these expeditions not to consider this as a serious part of an emergency package for any crew that's going somewhere. Because it's lightweight, it can be powered by a couple of solar panels, and it will just make sure you're connected, and then you set it up in 5 minutes. Yeah, so that's it. Thank you very much.
Thanks, JP. Thanks to Britt and Bo and and Kylie and Tracy and everyone, and for you guys for coming. So I'll just leave you with this. JP kind of alluded to it before. The why, right, of why we support this type of basic research. Yeah, insurance companies can make money by lowering their premiums or increasing their premiums about what happens, but why does the DoD care? Why does the Air Force care? We talked about this at lunch today, and really it comes down to what's the mission of the DoD, which is to identify where the risky places are, where the potentials for conflict are, and climate change can drive conflict. Climate change that drives a sea level rise. 50% of all human populations are located on the coast near sea level, right? If you have 4 billion people across the world moving inland, fighting over resources, fighting over land, fighting over territory, that is something the DoD wants to know what to do if and when that happens, right? And so that's why the DoD itself is interested. If you look in like the communications handbook for the big Department of Defense, one of those things is monitoring climate change and trying to find a way to deal with it. That's why we care, right? So be proud of the fact that we support basic science and that we are increasing the knowledge of human civilization. But on the other side, know that there's a practical application to what we're doing. So again, thank you guys for coming. I'm glad you showed up, and hopefully you guys learned something.